In physics, an inertial frame of reference is a frame of reference that describes time and space homogeneously, isotropically, and in a time-independent manner. All inertial frames are in a state of constant, rectilinear motion with respect to one another. An accelerometer moving with any of them would detect zero acceleration. Measurements in one inertial frame can be converted to measurements in another by a simple transformation. In general relativity, in any region small enough for the curvature of space-time and tidal forces to be negligible, one can find a set of inertial frames that approximately describe that region. Physical laws take the same form in all inertial frames. By contrast, in a non-inertial reference frame, the laws of physics vary depending on the acceleration of that frame with respect to an inertial frame, and the usual physical forces must be supplemented by fictitious forces. For example, a ball dropped towards the ground does not go exactly straight down because the Earth is rotating. Someone rotating with the Earth must account for the Coriolis effect, in this case thought of as a force, to predict the horizontal motion. Another example of such a fictitious force associated with rotating reference frames is the centrifugal effect, or centrifugal force. Introduction. The motion of a body can only be described relative to something else, other bodies, observers, or a set of space-time coordinates. These are called frames of reference. If the coordinates are chosen badly, the laws of motion may be more complex than necessary. For example, suppose a free body is at rest at some instant. In many coordinate systems, it would begin to move at the next instant, even though there are no forces on it. However, a frame of reference can always be chosen in which it remains stationary. Similarly, if space is not described uniformly or time-independently, a coordinate system could describe the simple flight of a free body in space as a complicated zigzag in its coordinate system. Indeed, an intuitive summary of inertial frames can be given as: in an inertial reference frame, the laws of mechanics take their simplest form. In an inertial frame, Newton's first law is satisfied. Any free motion has a constant magnitude and direction. Newton's second law for a particle takes the form, with F the net force, m the mass of a particle, and the acceleration of the particle, which would be measured by an observer at rest in the frame. The force F is the vector sum of all real forces on the particle, such as electromagnetic, gravitational, nuclear and so forth. In contrast, Newton's second law in a rotating frame of reference, rotating at angular rate omega about an axis, takes the form, which looks the same as in an inertial frame, but now the force F is the resultant of not only F but also additional terms, where the angular rotation of the frame is expressed by the vector omega pointing in the direction of the axis of rotation, and with magnitude equal to the angular rate of rotation omega. Symbol times denotes the vector cross product. Vector xb locates the body and vector vb is the velocity of the body according to a rotating observer. The extra terms in the force F are the fictitious forces for this frame. These terms all have these properties. They vanish when omega equals 0, that is, they are 0 for an inertial frame. They take on a different magnitude and direction in every rotating frame, depending upon its particular value of omega. They are ubiquitous in the rotating frame, and they have no apparent source in identifiable physical sources, in particular, matter. Also, fictitious forces do not drop off with distance. For example, the centrifugal force that appears to emanate from the axis of rotation in a rotating frame increases with distance from the axis. All observers agree on the real forces, F. Only non-inertial observers need fictitious forces. The laws of physics in the inertial frame are simpler because unnecessary forces are not present. In Newton's time, the fixed stars were invoked as a reference frame, supposedly at rest relative to absolute space. In reference frames that were either at rest with respect to the fixed stars or in uniform translation relative to these stars, Newton's laws of motion were supposed to hold. In contrast, in frames accelerating with respect to the fixed stars, an important case being frames rotating relative to the fixed stars, the laws of motion did not hold in their simplest form, but had to be supplemented by the addition of fictitious forces, for example, the Coriolis force and the centrifugal force. Two interesting experiments were devised by Newton to demonstrate how these forces could be discovered, thereby revealing to an observer that they were not in an inertial frame. The example of the tension in the cord linking two spheres rotating about their center of gravity, and the example of the curvature of the surface of water in a rotating bucket. In both cases, application of Newton's second law would not work for the rotating observer without invoking centrifugal and Coriolis forces to account for their observations. As we now know, the fixed stars are not fixed. Those that reside in the Milky Way turned with the galaxy, exhibiting proper motions. Those that are outside our galaxy participate in their own motion as well, partly due to expansion of the universe, and partly due to peculiar velocities. The concept of inertial frames of reference is no longer tied to either the fixed stars or to absolute space. Rather, the identification of an inertial frame is based upon the simplicity of the laws of physics in a frame. In particular, the absence of fictitious forces is their identifying property. In practice, although not a requirement, using a frame of reference based upon the fixed stars as though it were an inertial frame of reference introduces very little discrepancy. For example, the centrifugal acceleration of the Earth because of its rotation about the Sun is about 30 million times greater than that of the Sun about the galactic center. To illustrate further, consider the question, does our universe rotate? To answer, we might attempt to explain the shape of the Milky Way galaxy using the laws of physics, like the anisotropy of the microwave background radiation or Big Bang nucleosynthesis. Just how flat the disk of the Milky Way is depends on its rate of rotation in an inertial frame of reference. If we attribute its apparent rate of rotation entirely to rotation in an inertial frame, a different flatness is predicted than if we suppose part of this rotation actually is due to rotation of the universe and should not be included in the rotation of the galaxy itself. Based upon the laws of physics, a model is set up in which one parameter is the rate of rotation of the universe. If the laws of physics agree more accurately with observations in a model with rotation than without it, we are inclined to select the best fit value for rotation, subject to all other pertinent experimental observations. If no value of the rotation parameter is successful and theory is not within observational error, a modification of physical law is considered. So far, observations show any rotation of the universe is very slow, and debate persists over whether there is any rotation. However, if rotation were found, interpretation of observations in a frame tied to the universe would have to be corrected for the fictitious forces inherent in such rotation. Evidently, such an approach adopts the view that an inertial frame of reference is one where our laws of physics apply. When quantum effects are important, there are additional conceptual complications that arise in quantum reference frames. Background: a brief comparison of inertial frames in special relativity and in Newtonian mechanics, and the role of absolute space is next. A set of frames where the laws of physics are simple according to the first postulate of special relativity. All physical laws take their simplest form in an inertial frame, and there exist multiple inertial frames interrelated by uniform translation. Special principle of relativity: if a system of coordinates k is chosen so that, in relation to it, physical laws hold good in their simplest form, the same laws hold good in relation to any other system of coordinates k, moving in uniform translation relatively to k. Albert Einstein. The foundation of the general theory of relativity. Section A. 1. The principle of simplicity can be used within Newtonian physics as well as in special relativity. See Nagel and also Blagojevich. The laws of Newtonian mechanics do not always hold in their simplest form. If, for instance, an observer is placed on a disk rotating relative to the Earth, she will sense a force pushing him/her toward the periphery of the disk, which is not caused by any interaction with other bodies. Here, the acceleration is not the consequence of the usual force, but of the so-called inertial force. Newton's laws hold in their simplest form only in a family of reference frames, called inertial frames. This fact represents the essence of the Galilean principle of relativity. The laws of mechanics have the same form in all inertial frames. Milutin-Blagojevich. Gravitation and gauge symmetries. 4. In practical terms, the equivalence of inertial reference frames means that scientists within a box moving uniformly cannot determine their absolute velocity by any experiment. According to this definition, supplemented with the constancy of the speed of light, inertial frames of reference transform among themselves according to the Poincare group of symmetry transformations, of which the Lorentz transformations are a subgroup. In Newtonian mechanics, which can be viewed as a limiting case of special relativity in which the speed of light is infinite, inertial frames of reference are related by the Galilean group of symmetries. Absolute space. Newton posited an absolute space considered well approximated by a frame of reference stationary relative to the fixed stars. An inertial frame was then one in uniform translation relative to absolute space. However, some scientists, even at the time of Newton, felt that absolute space was a defect of the formulation, and should be replaced. Indeed, the expression inertial frame of reference was coined by Ludwig Lange in 1885, to replace Newton's definitions of absolute space and time by a more operational definition. As translated by IRO, Lange proposed the following definition: a reference frame in which a mass point thrown from the same point in 3 different directions follows rectilinear paths each time it is thrown, is called an inertial frame. A discussion of Lange's proposal can be found in Mach. The inadequacy of the notion of absolute space in Newtonian mechanics is spelled out by Blagojevich. The existence of absolute space contradicts the internal logic of classical mechanics since, according to Galilean principle of relativity, none of the inertial frames can be singled out. Absolute space does not explain inertial forces since they are related to acceleration with respect to any one of the inertial frames. Absolute space acts on physical objects by inducing their resistance to acceleration, but it cannot be acted upon. Milutin-Blagojevich. Gravitation and gauge symmetries. 5. The utility of operational definitions was carried much further in the special theory of relativity. Some historical background including Lange's definition is provided by Dissel, who says in summary, the original question, relative to what frame of reference do the laws of motion hold, is revealed to be wrongly posed. For the laws of motion essentially determine a class of reference frames, and a procedure for constructing them. Robert Dissel. Space and time. Inertial frames. Newton's inertial frame of reference. Within the realm of Newtonian mechanics, an inertial frame of reference, or inertial reference frame, is one in which Newton's first law of motion is valid. However, the principle of special relativity generalizes the notion of inertial frame to include all physical laws, not simply Newton's first law. Newton viewed the first law as valid in any reference frame that is in uniform motion relative to the fixed stars, that is, neither rotating nor accelerating relative to the stars. Today the notion of absolute space is abandoned, and an inertial frame in the field of classical mechanics is defined as an inertial frame of reference is one in which the motion of a particle not subject to forces is in a straight line at constant speed. Hence, with respect to an inertial frame, an object or body accelerates only when a physical force is applied, and, in the absence of a net force, A body at rest will remain at rest and a body in motion will continue to move uniformly, that is, in a straight line and at constant speed. Newtonian inertial frames transform among each other according to the Galilean group of symmetries. If this rule is interpreted as saying that straight-line motion is an indication of zero net force, the rule does not identify inertial reference frames because straight-line motion can be observed in a variety of frames. If the rule is interpreted as defining an inertial frame, then we have to be able to determine when zero net force is applied. The problem was summarized by Einstein. The weakness of the principle of inertia lies in this, that it involves an argument in a circle. A mass moves without acceleration if it is sufficiently far from other bodies. We know that it is sufficiently far from other bodies only by the fact that it moves without acceleration. Albert Einstein. The meaning of relativity. 58. There are several approaches to this issue. One approach is to argue that all real forces drop off with distance from their sources in a known manner. So we have only to be sure that a body is far enough away from all sources to ensure that no force is present. A possible issue with this approach is the historically long-lived view that the distant universe might affect matters. Another approach is to identify all real sources for real forces and account for them. A possible issue with this approach is that we might miss something, or account inappropriately for their influence, perhaps, again, due to Mach's principle and an incomplete understanding of the universe. A third approach is to look at the way the forces transform when we shift reference frames. Fictitious forces, those that arise due to the acceleration of a frame, disappear in inertial frames, and have complicated rules of transformation in general cases. On the basis of universality of physical law and the request for frames where the laws are most simply expressed, inertial frames are distinguished by the absence of such fictitious forces. Newton enunciated a principle of relativity himself in one of his corollaries to the laws of motion. The motions of bodies included in a given space are the same among themselves, whether that space is at rest or moves uniformly forward in a straight line. Isaac Newton. Principia, Corollary v. 88. In Andrew Mott translation, this principle differs from the special principle in two ways. First, it is restricted to mechanics, and second, it makes no mention of simplicity. It shares with the special principle the invariance of the form of the description among mutually translating reference frames. The role of fictitious forces in classifying reference frames is pursued further below.